In this video, we are starting our section on substitutions and change of coordinates. Our goals are to evaluate complicated double integrals using what's called a change of coordinates, and to recognize when doing this change of coordinates is helpful. So in this video, we are going to introduce this method of how we can evaluate double integrals using change of coordinates. Sometimes it's possible to convert complicated integrals into a form that's easier to evaluate. And we can do this by using a change of coordinates. So a change of coordinates. Or sometimes we call this a transformation or a substitution. To simplify the integrand, that's the thing we are integrating, or the limits of integration, maybe to simplify those, or maybe both. So let's look at simple examples to explore how this is going to work. So let's say that I'm given the following double integral, and I want to use the coordinate change, meaning I'm going to substitute by letting x equal 2u and y equal 3v to rewrite this double integral in terms of u and v. So first off, the region of integration that I have here, the inner integral has a dx, and x goes from 0 to 2. The outer one is dy, which goes from 0 to 3. So because those are all constants, this is a rectangle. So x goes from 0 to 2, y goes from 0 to 3. So we are talking about this rectangle here. This rectangle, I'm going to call that R. That's the region that we're integrating over in our xy plane, the region R. So after we do this substitution, what are these limits of integration going to be in terms of u and v? To figure that out, we can take these values, like this is x equals 0, and I can plug it into this substitution. So for example, if I take x equals 0, and I plug it into x equals 2u, we're going to get that 0 equals 2u, and then dividing by 2, I get that u equals 0. Nice. Okay, so if I do the same thing for x equals 2, and I take that and I plug it into this equation, I would get that 2 equals 2u, and then dividing by 2, I get that u equals 1. Okay, nice. So if I draw my u, v axes, I now know that u goes from 0 until 1. If we do the same thing with these limits of integration for y, we have y equals 0 and y equals 3. And if we plug those into this substitution, so if I plug 0 into that, I would get that v equals 0. And if you plug 3 into that, we'd get v equals 1. So v, on my v-axis, v goes from 0 to 1. So we're going to get this rectangle, this smaller rectangle, where the side lengths are just 1. Okay, so I'm going to call this smaller rectangle G. Okay, G. This is the new region that I would integrate over in the UV plane. Okay, so how does my double integral change when I switch variables and do this substitution? Well, my function f. Now I know what x is. I know x is 2u, and I know y is 3v. So those we're going to just sub in. So wherever we see x, we're going to sub in 2u. Wherever we see y, we are going to sub in 3v. Okay, my limits of integration are going to change. So if I decide to put du on the inside, I need the u values on the inside. So u, we just saw, goes from 0 to 1, 0 to 1. And v on the outside, the v values we also saw go from 0 to 1. V goes from 0 until 1. What I still need to know is, well, when I do this substitution and I convert to u and v, what's the relationship between dx dy and du dv? Okay, this is the analog of when we do u substitution. Like change of coordinates is like u substitution, but for double integrals. So if I do a u substitution, like u equals x cubed, normally I would now do the derivative and get du equals 3x squared dx. And we plug that in when I'm doing my integral and switching it. So how does that work here? Well, if I look at this original region and I think about its area, so the area is based on this base, which I will call dx, times this height, which I'll call dy. And if I compare that area to the area of this new rectangle, so this area is based on this base, which I'll call du, times this height, which I'll call dv. And just comparing those two, the original area is 6, and this new area is 1. So this original area is dx dy is 6 times du dv. So dx dy equals 6 times du dv, which means this factor, this 6, needs to go here. And that term 6 is what's called the Jacobian. So conceptually, what's going on here? When I'm doing this substitution, this original region of integration, which had area 6, it's shrunk down and it's 6 times as small. So putting in this extra factor of 6 balances that out. Okay, so what's the general formula here? So when I'm doing a change of coordinates and I substitute by letting x be equal to some function, I'm going to call it g, a function, and it could be in terms of u and v, even though in this formula it was just with a u. And y is going to be some function h of u and v, even though here it was just in terms of v. It could also have u's in it. Now, my double integral, where the x is, I'm going to sub in this formula for x. And where the y is, I'm going to sub in this formula for y. And then I'll get a du and a dv. And then there's an extra factor, like the 6, that pops out. And that's called the Jacobian, which I call j of u comma v. And you end up taking the absolute value of it. So what's the Jacobian? The Jacobian, the way I notate it and write it is I write this kind of partial derivative, x comma y, partial u comma v. That's just notation. What it means is this thing. This is called the determinant of a matrix. So on the first row of the matrix, you have partial derivatives of x with respect to u and v. On the second row, you have partials of y with respect to u and v. These vertical lines mean you're taking a determinant. So I don't expect that you've seen this before. So let's talk about what this equals. What you do is you multiply these two diagonal entries together. So you'll get the partial of x with respect to u times the partial of y with respect to v. And then you subtract what you get when you multiply the other two diagonal entries together. So the partial of x with respect to v times the partial of y with respect to u. And that's my formula for the determinant of, this is called the 2 by 2 matrix. Okay, so let's use this for our example. So in the example we just did with this substitution, our Jacobian j of u comma v, what would that equal? So I'll write this determinant, this vertical line indicates determinant. And then on the first row, I got to do the partials of x with respect to u and v. So x equals 2u. The partial of that with respect to u would just be 2. When I do the partial with respect to v, well, u gets treated as a constant. So that derivative would be 0. And then I do the partials of y. So first with respect to u, so v gets treated as a constant. That would be 0. The partial of this with respect to v would be 3. Nice. Okay, so now doing the determinant, you multiply these two diagonal entries. So that gives me 2 times 3. And then subtract what you get when you multiply the other two diagonal entries. So 0 times 0, which is 6. And then we'd have to absolute value this thing. So absolute value of my Jacobian is the absolute value of 6, which is 6. Okay, so let's do an example. Let's say that I want to evaluate this double integral, where R is the region in the xy plane that's bounded by these 4 equations. I want to evaluate this by applying the transformation given by these 2 equations and integrating over an appropriate region in the UV plane. So the first step of this is to sketch the region of integration R, the original one, in the xy plane. So, okay, all 4 of these are lines. So y equals x has slope of 1, and it goes through the origin. So here's 1 on the y-axis, Here's one on the x-axis. So it'll go through the origin and also go through the point 1, comma 1. So that's my y equals x. Y equals x minus 1 also has slope 1, but the y-intercept is down at -1 now. So it just gets shifted down 1 unit. So that is something like this. Y equals x minus 1. Y equals -1/2 x also goes through the origin, but it has a slope of -1/2. So that would look something like this. Okay, that is y equals -1/2 x. And then the final equation adds 1 to that, so it shifts the whole thing up 1 unit. It has a y-intercept of 1. So if I draw that, it looks something like this. So that is y equals 1 and then -1/2 x. Okay, so my region of integration, R, is this region here. This kind of parallelogram region. So, one of the reasons why doing this double integral just directly isn't super easy is if I look at this region of integration, regardless of whether I slice this thing vertically like this, notice that the top function and the bottom function change. Like here, the top function is y equals x, and here the top function is based on this equation. So the same thing happens for the bottom functions. The bottom functions change. So if I were to slice it vertically, I would have to split up my integral into at least 2 double integrals. I'd have to split it up here at this vertical slice. Even if I slice this thing horizontally, well, the function on the left changes, and the function on the right also changes. So I'd have to split that up into multiple double integrals. And if I can avoid that, that would be nice. The other reason why this is not easy to evaluate directly is just this function isn't the easiest thing to integrate. It'd be simpler if I just had like x on top or just like y on the bottom or something like that. So that's one of the reasons why I'd try a change of variables. Okay, so the next step is to then sketch the corresponding region G after we've done the substitution in the UV plane. So how do we do that? Okay, so it turns out that I'm going to now take my equations, which are u equals x plus 2y, and then v equals x minus y, and then I'm going to isolate the x and the y in these equations. We'll need that later for the Jacobian. So I'm going to take this system of equations, and I notice that they both have an x, so if I subtract them, on the left, I'll get u minus v. On the right, the x's cancel, and I'll get 3y. Nice, so if I divide 3, I'll get y equals u minus v over 3. So I can take that, and I can sub it into one of my equations. So like, if I sub that into the second equation, I would get that v equals x minus y, and y is u minus v over 3. So let's isolate x. So maybe I'll write x first. And then if I add this fraction to the other side, I'll get v plus u minus v over 3. And if I get a common denominator, this becomes 2v plus u over 3. So highlighting my formulas, I have y equals this, and I have x equals this fraction. Okay, so we'll use these in a sec. So what I want to do now is I want to convert my original region R in terms of my new variables u and v. So I'm going to organize that work into this table. So I'm going to look at each side of this boundary and convert it to my new boundary for my new region. So the equations for the original boundary, one of those equations is y equals x. One of them is y equals x minus 1. Then I have y equals -1/2 x. And y equals 1 and then -1/2 x. So there's a couple ways to figure out what these are going to be in terms of u and v. So one of those ways is to try to do some algebra on these equations so they end up looking more like what I see in my substitution. So I noticed that if I subtract the y over to the right, we are going to get 0 equals x minus y. And I see here that x minus y equals v. So this means that 0 equals v. And that is my new equation. It's v equals 0. That's a much simpler equation. Okay, if we do the same thing with this next equation, if I rearrange it, I can move 1 to the left and the y to the right to get x minus y. And then this becomes 1 equals, and x minus y is v. So I get v equals 1. Nice, v equals 1. Okay. If we do the same thing for this next equation, this one ends up looking like the equation for u if I multiply the 2 over. So if I multiply the 2 over and then I add the x, you'll get 2y plus x equals 0. And 2y plus x is u. So this becomes u equals 0. So this becomes u equals 0. Nice. And then if I do the same thing in the last one, I'm going to trust that we can do that. But if you do, you'll get that u equals 2. Okay, u equals 2. Okay. So if I now take these equations and I sketch them in the UV plane, I'm going to make the u-axis this horizontal one, the v-axis this vertical one. Okay, so u goes from 0 to 2, v goes from 0 to, I'm putting 1 up here. Okay, so I'm going to get this rectangle. This rectangle, this is my new region G in the UV plane. Okay, so that's one way I can get these new equations for my new boundary. There's another way that's a bit more systematic, although it can be longer. And this more systematic way works even if I can't like rearrange these equations to kind of perfectly match up with my substitution. And we need this sometimes. So how does this work? So we take these equations that we just got for y and for x, and you sub them in to this equation. So if I do that, y equals u minus v over 3. And that's going to be equal to x, and x equals this. X equals 2v plus u over 3. And now let's simplify. So I can multiply by 3, both sides by 3, and I get u minus v equals 2v plus u. I could subtract u from both sides, they cancel. And I'll get that 0 equals 3v. And then dividing, I get v equals 0, the same thing. Okay. If I do the same thing for this next equation, I get y on the left, which is u minus v over 3. That equals x minus 1. So x is 2v plus u over 3, and then minus 1. If I multiply both sides by 3, we get u minus v equals 2v plus u, and then minus 3. Ooh, don't mean to erase that, minus 3. I can cancel the u's from both sides. And if I rearrange this, so you get 3 equals 3v. And then dividing 3, you'll get v equals 1. Nice. Okay, so we could do the same thing for these other two equations if we wanted to. I'm going to skip that for this problem. But we'll see an example later where we really do need to do it this way, where it's not as easy to just algebraically manipulate all the equations to make them look like my substitution. Okay, so what do we do from here? Now that we know the region of integration, now we're ready to get the Jacobian. So step 3 is we're going to find the Jacobian. So remember, the Jacobian, j of u comma v, is the absolute value. It's the determinant of, you take the partials of x. Up top, partial of x with respect to u, times the partial of x with respect to v. And then the partials of y on the bottom. The partial of y with respect to u, times the partial of y with respect to v. Okay, close that determinant. So now let's do those partial derivatives. So I've gone ahead and written down my equations for x and y. This is actually one of the reasons why I need x and y isolated, so I can do these partial derivatives. So I can simplify this. I can split this up into two fractions. This becomes 2/3 v plus 1/3 u. So if I do the partial of this with respect to u, I get just 1/3. If I do the partial of that with respect to v, we get 2/3. Okay. And if you do the partials of y now, with respect to u, we'll get 1/3. With respect to v, we'll get negative 1/3. So now we can do the determinant. So we multiply these two diagonal entries first. That gives us negative 1/9. And then we subtract. We subtract what we get when you multiply the other two diagonal entries, the off diagonal entries. So that gives me 2/9. And then subtracting, we get negative 3/9, which is negative 1/3. And then I have to absolute value that. So the absolute value of j of u comma v is just 1/3. Okay, so now we're ready for the last step, which is now we can rewrite the integral and evaluate it. So I'm going to get a new double integral where, well, what was x plus 2y? From my substitution, x plus 2y was u. And on the bottom, I have x minus y, and that's v. That's actually one of the reasons why we substituted that. So the x plus 2y on the top is just u. And then I have a square root of x minus y, we just saw was v. So doing that substitution makes the numerator and denominator drastically simpler. So that's going to get multiplied by the Jacobian, its absolute value. So the absolute value of Jacobian, which we just saw was 1/3. And then because my new region of integration is just a rectangle, it doesn't really matter if you do u inside or v inside. So maybe I'll just do du on the inside and then dv on the outside. And then my limits of integration for u were from u equals 0 to u equals 2. And then for v, they go from v equals 0 to v equals 1. Okay, so this 1/3 is just a constant multiplying my function. I can just factor that out to the front. And then the remaining function, I can split up as a product of u times 1/√v. So because you can separate it into a product of something with just u's and something with just v's, and these limits of integration are just all constants, I can decouple this integral. I can split it into a product of the integral that just has the v's, which goes from 0 to 1, 1/√v dv, times the integral of just the u portion. That goes from 0 to 2 of u du. Okay, so now we're in business. We're almost there. 1/√v, well, that simplifies to v to the negative 1/2. So now I can do that antiderivative. We got the 1/3 in front. So I add 1 to the power, I get v to the positive 1/2. I would divide by 1/2, but that's the same as multiplying by 2. And then I plug in the 0 and the 1. Antiderivative of u is u squared over 2. And then I'd plug in the 0 and the 2. Nice, I'm ready to plug in. So I get 1/3 in front. I know v to the 1/2 is square root of v. So this becomes 2 squared of v. If I plug in 1, we'll get 2, and then minus. If you plug 0 in, you'll get 0. Similarly, if you plug into this next term, you'll get 2 minus 0. And then multiplying this out, we get 4/3. And that's the value of our integral. So just to recap, what were some of the indicators that doing the substitution was going to be helpful? So one was, this integral right now is hard to do. And making this substitution in particular makes the numerator just become u, and the denominator becomes square root of v. And that's definitely a lot simpler. The other indicator that this particular substitution was helpful was to notice that, well, these equations, these boundary equations, they actually have this form as well. If you rearrange them, two of them involve an x minus y, which is what we were seeing show up in the integral as well. And two of them involve a 2y plus x, which we were also showing up in the integral. So when that happens, when the boundary curves kind of have the same type of format, and especially when that same type of format shows up in the integral, that's a big tip-off to try this substitution, this change of variables. So in terms of our goals for this section, we finished goal 1, learning how we can evaluate complicated double integrals using a change of coordinates.